All right, so yeah, it's really nice to be here and having the chance to talk to all of you. At first, I was really worried that my talk is going to be really nerdy, but the previous speaker actually set the bar really high. I'm going to talk about something called metastable failures. Right, so broadly speaking, this is a class of performance failures. And everything usually starts normal, right? So we have some kind of system. It may be somewhat predisposed to some kind of failure, right? But everything is working fine until some kind of trigger comes in and blows the system over the hump, right? So this is already bad because we can crash the system. So this is not metastable failure yet, and this is not as bad as it gets. Typically, we design our systems, our software, to be resilient and to be fault tolerant, right? So ideally, when we remove that trigger, when the wind stops blowing, our system should just sprint back up and continue running. But that's not what happens in metastable failures, because most systems tend to have some mechanisms that actually keep everything not normal, even after the trigger is removed. So I'm going to go and kind of talk about a hypothetical example, right? So let's pretend we have a toy system that has a capacity to serve 1,000 requests per second. And under normal conditions, we are serving about 750 requests per second, right? So we're getting pretty high to the capacity of the system, but not over the board yet, right? So, and this system is in what I call metastable vulnerable state. Some trigger comes in, and that trigger can overload the system, right? So in my example here, maybe the trigger is some kind of unexpected load spike, right? So I call this an expectation failure, right? So you didn't anticipate some kind of behavior from outside of your system that causes that load spike. But triggers can come in all kinds of different flavors, right? That can be like hardware failures, software failures, bugs in your code, you name it. So this is already a bad situation to be in, right? So we are overloaded, it's not pretty. But it gets worse, because now we have this hidden mechanism, right? Or more than one mechanism that takes that overload, takes that bad situation, and continuously makes it worse, right? So I call this amplification, or sometimes I call them sustaining effects. But what they tend to be are some kind of positive feedback loops that feed on your bad state, right? So when your system is already in a bad state, they start to feed on that bad state and make it even worse. One example I can give you is garbage collection induced amplification loop, right? So if we have a system with this sudden spike of load, this additional requests are going to go to the system. They will queue up somewhere. This larger queue may, if it's big enough, it may create substantial memory pressure. It may cause garbage collection. Garbage collection will use the resources of your system, which means now you have less capacity to do actual useful work, which means more stuff is going to queue up, create more memory pressure, and we complete the loop, and we can repeat and repeat and repeat, and amplify this bad situation to make it much, much, much worse. So what happens when we fix the initial trigger problem? If we have been stuck in this loop for quite some time, nothing good happens, actually, right? So the system remains failed. The system cannot serve any useful work. The good put remains at 0 because we over-amplified this problem, our initial problem, so much that fixing that initial trigger problem just has no impact. So this is what I call metastable failure. So getting out of metastable failures is pretty easy. We just need to kill all the load, right? So usually that literally translates to turning it off and on again. And as you can imagine, it's not an easy thing to do if you're running a large system, right? So it's much better to try to stay away from metastable failures. So here I show a life cycle type diagram of metastable failures, right? So we start in this good, somewhat predisposed to failure state called metastable vulnerable. And then if we have big enough triggers, we can get into the overload. If that overload condition is sustained for quite some time, if the trigger is not removed quickly enough, we will have the sustaining effect, the amplification loop kick in. And if that runs for very long, then we end up in metastable failure state. And then out of that, just reduce the load until you get into some kind of stable state. Right? So stable state is the state of the system where the amplification mechanisms cannot essentially amplify the problem beyond the capacity of your system. Right? We almost never run systems in a stable state because that will be too expensive. Right? So most larger systems, they will operate in metastable vulnerable state. And it's OK. Right? So yes, we have a risk of having those triggers, start all of these amplification processes and develop in a metastable failure, but it's OK. Right? And we can try to mitigate some of the risks of being in metastable vulnerable state. So in the rest of my talk, I will kind of briefly describe my 3 pillars of being OK in metastable vulnerable state. The first pillar, the first cornerstone is understanding your environments, algorithms that you use like in your systems, right? Understanding your systems really well and understanding workloads. Now, I'm not going to pretend that we can understand everything about our environments, systems, and workloads, right? But having more understanding is the key. The second pillar, I call it trigger-resistant design or trigger-resistant architecture. So once we understand how our environments and systems and algorithms that underpin those systems work, we can actually do something about some of the common triggers, right? And the third cornerstone, the third pillar is protection of vulnerable components, right? So it happens to be the case that not every part of your system is susceptible to metastable failures in the same way. Some are more vulnerable, some are more susceptible to failures, and we can do something about protecting them. So let's talk about understanding stuff. Right? So knowledge is power. And if we understand more about what's going on in our environments, systems, and what workloads we use, we can avoid something I call expectation failures. Right? So these expectation failures, they arise from the mismatch between the environment's capabilities and the system's needs. So I'm going to go and kind of do an example here. Right? So in one of my classes last year, my students studied cloud latency, essentially the latency of some applications interacting in the cloud. Right? So cloud is a very big and very important environment, right? There's like so many dimensions to learn about, right? It's all about like shared resources, noisy neighbor syndrome, et cetera, et cetera. Knowing how well a cloud performs is crucial for configuring systems that run in a cloud. And just like one of the many dimensions of cloud environment is how quick you can talk in a cloud, right? And if we just look at that latency of maybe having like one VM talking to another VM, an app on one VM talking to an app on another VM, that number, even that number is not that straightforward, right? Because it like involves a bunch of stuff like in between, right? The cloud network, what hardware is there, what hypervisors are doing, what happens at the OS kernel, unless you're using like kernel bypass and whatnot, and finally, your app, right? How busy your app, if you have any queuing going on, and so on. So even that is incredibly complicated. But I look at the most kind of trivial thing, like end-to-end latency. Can I measure the latency between two like little pieces of code running in two different VMs in the same availability zone? right, of the same region of a cloud. And would you expect to see latency spikes that are 3,000 times over the median latency? Like, they don't fit on the graph here, right? So those two spikes, they're like, I had to cut them because if I had to fit them on the graph, it will go through the roof, right? But that's something that we have observed. Some like very stable, latency, and some really, really big spikes, right? So that is something to potentially anticipate when we think about systems and algorithms that will run in those clouds. Would you expect a lot of variation and some 20 minutes cycles that seem to appear in this cloud? So this is a different cloud provider. I'm not naming them, but this is like another observation, right? So much more variable, maybe not having those like couple huge spikes, but a lot of like smaller yet very substantial variability and some kind of cyclical patterns, right? So this variability, these cyclical patterns, they can create high tail latency in that particular cloud, right? So this figure right here shows essentially the distribution of the latency, right? The CDF. And I'm showing like the top 5% of observations. And in this blue cloud, which I'm not going to name, the 95th percentile latency was more than a millisecond. Their median latency in that particular scenario on the VMs that I used, was like all the stuff that we used, that median latency was like half of that. But if you look at the 99th percentile, it's like above 3 milliseconds. That's really bad, right? And those things, they play into like what kinds of systems we can run, or what kinds of systems, like how we need to configure the systems to run in those clouds, right? I'm looking at just one dimension here, though. But if we have a system that expects low latency, right, it will surely work better in cloud number 1, which has like 99 percentile latency of 400 microseconds, versus cloud number 2 that has 99 percentile latency of 3.1 milliseconds. So, in this case, we can have that latency expectation mismatch, right? So the app, the system expects low latency, but the environment cannot provide it. So once we understand our environments better, right, we also need to understand how algorithms, how systems, will use that environment, right? What do systems expect, right? Can the environment, satisfy those expectations? Can they configure the systems to match the expectations, to match the environment better? This, by the way, is the image of how AI thinks about an abstract algorithm. So again, I'm going to look at the example, right? So something that is very close to my research. Like in a lot of my work, I study stateful systems. I study replication, transactions, and so on. So there is a class of algorithms called state machine replication that underpin a lot of stateful systems, right? Pretty much most of the storage systems, configuration systems, etcd, zookeeper, you name it. And what happens is that some algorithms in this category, they perform decently well when we have networks with like flaky latency, right? So some algorithms, they will kind of inherit that latency flakiness, but they will not suffer in terms of like throughput degradation or capacity degradation. They will continue like providing like useful throughput, useful work, right? And there is another class of algorithms that expects certain timing assumptions from your network, from message delivery. And when that happens, they will start to degrade not only the latency when there is a flaky latency, but also the throughput of the system, right? So in this figure, I show one algorithm from each category. So multipaxes, And it's more modern cousin Raft. They are used in a lot of modern state-of-the-art systems, right? So multipaxos underpins the replication in DynamoDB. It's used in Google Spanner. Raft algorithm, which is very similar to multipaxos, is used in CockroachDB, YugabyteDB, like a bunch of really large distributed stateful systems. Now, Rabia in this example is an academic algorithm, right? So it is not something that, as far as I know, has been used in any kind of production system. And you can probably guess why, right? Its performance degrades if I start to introduce the flakiness. So on the x-axis here, I show the delay that I introduced to just one node out of 3 nodes in that toy setup. So both algorithms run on three VMs, 3 servers, and one of these servers has an artificial latency added to it, right? From anywhere from 0.1 milliseconds to 5 milliseconds, right? And it's not just 5 milliseconds; it's up to 5 milliseconds. So it's taken from a distribution. So, and we can see that the throughput normalized to the maximum throughput that a particular algorithm can provide, it barely changes in multipaxos, right? Only when we have a very, very high added delay to a single node, and in this case, in multipaxos, it was the most important node, the leader node, we start to see some throughput degradation. The Rabia, the other protocol, the academic protocol, on the other hand, fails pretty badly at that time. Now, I want to say that while this is an academic protocol, I have seen some of the ideas expressed in this algorithm, in this paper, taken into the open source, right? So, beware. The difference in performance of these algorithms is really that expectation mismatch, right? So Rabia, it is built on top of the assumption that the network is stable, that the message delivery can happen at about the same time across that cluster of 3 or 5 nodes that is part of a single a state machine replication instance, right? And it simply may not be the case. So another example I want to mention is transactional systems, right? So again, a lot of my work, a lot of my research is on stateful systems, databases, data stores, and so on. So transactions, are a big deal, right? And in the common case, right, if we have a lot of transactions, they will run concurrently if they have nothing in common, right? So no contention, no common keys, common objects that these transactions interact with, we can go very fast, right? So all of these transactions can go, in parallel. We can scale the system really well, right? But that doesn't work if we have hot objects, if we have hot data, right? If all of a sudden a good chunk of our transactions now have to depend on a single hot object or some smaller set of hot data, well, we create contention, right? And things will start to slow down. Depending on the type of transactional approach, transactional algorithm used in the system, the transactions will either abort and restart and retry, which will use the resources of your system without actually producing any useful work. Or the transactions will queue up, waiting for a lock. They wait to acquire a lock, and they will start to queue up and wait and wait and wait. Again, using the resources and not providing any useful work. So yeah, this is where I get into the kind of my next step of understanding, right? So we also need to understand the workloads, right? So in case of these transactional systems, we want to make sure that we want to know where the contention can arise, right? Like, what are the objects, what are the keys that can contend, that can create, those performance degradations for these algorithms that we use in these systems. But it's not the only, way to, it's not the only thing to know about the workloads, right? So there are a bunch of other things that will happen in your workloads. Do you have some kind of correlated events happening in your workloads? Do you, maybe explicitly or implicitly have like users or clients that coordinate on doing something at the same time that will create those unexpected load spikes that I was talking about before, right? So we need to understand the workload behaviors, better that may cause these algorithms or systems to trigger. So aside from, the contention, the hot objects, and so on, here is a real example that we saw when we were researching the original Metastable failure papers a couple years ago. And that example had a database, and on top of this database there was an application, right? And that app, that system, had a bunch of clients. And it happened to be the case that these clients were coded to do something on a timer once a day. And it happened to be the case that that timer was hard-coded, and they were doing that thing on a timer all at once, right? So if you have an active client that's online, they will interact with that system and will do something. To make things worse, that timed action was not a regular thing that the clients would do in application, and it happened to run a very expensive transaction. Right? Much more expensive than the typical interaction between the users and the back end of the application was in normal circumstances. And naturally, it crashed the database, right? Despite the fact that these people over-provisioned the database by the factor of 10. So yeah, this is just another example of why we want to really understand the workloads, what can happen. Do we have those, in this case, implicit waves of clients running to your system, right? But they can be unanticipated as well. So now, we gain some understanding, right? Again, I'm not pretending that we can understand everything about the environments, algorithms, and workloads, but if we understand more, we can start thinking about the ways to mitigate some of the risks of actually becoming metastable failure, right? And I want to think about trigger resistance, right? So we cannot avoid those triggers, right? You cannot avoid crazy electrician cutting the wires and crashing a bunch of servers. But maybe we can design the systems to tolerate some common triggers better, right? And the very first step in doing this is avoiding the expectation mismatches that we talked about in the understanding part of this talk, right? So if we know what the environment can provide, and if we know what the algorithms that underpin our systems expect from that environment, then maybe we can avoid those expectation mismatches, right? Again, I'm not going to pretend that we can avoid all of them because we can not understand everything. But within the understanding that we have gained, right, we can try to avoid the expectation mismatches. So one example I can give you is aggressive timeouts and flaky network, right? Going back to the previous examples. So if we have a system that maybe is configured for a very aggressive timeouts to reconfigure in case of a failure, so that they provide potentially low latency to their clients, their users. Well, if you misconfigure those timeouts for your environment, you may end up in a situation where those timeouts cause a lot of false positives on those failure detectors, right? So if my 99th percentile latency is 3 milliseconds and 99.9 was 5 or 6 milliseconds, that's a lot, right? So the false positives on failure detectors will cause the systems to undergo unnecessary reconfigurations or recoveries, right? Nothing really failed, only our expectations have failed. But the system will react to this, by doing those recoveries or reconfigurations as if something real failed. And while doing so, it will use the resources, right? It will, like those reconfigurations, they're not cheap. Changing the leader in a stateful application is not cheap. So it will expend the resources that could have been used for the real useful work. So step 2, well, maybe we can start designing the systems and the algorithms that underpin those systems, with better fault tolerance in mind, right? So many, if not all, algorithms that we use are designed for fault tolerance. There is a problem, though. Many are designed by academics, right? And we are somewhat detached from the reality. And we may end up in a situation where the algorithm is fault tolerant on paper, right? I call this algorithmic fault tolerance. An algorithm that may underpin your system can safely tolerate the failures, right? So, hey, there is not going to be data loss. That's great. The consistency is going to be maintained. That's great. But by the way, I cannot do it under load, right? So if that failure happened, I'm going to stop to a crawl. The example here is of another state machine replication algorithm called Menzies, which is a popular academic algorithm. I'm not sure if anyone actually has used it in practice. But in its kind of basic form, as described by the academics, if you implement this, if you run this protocol, if you run the state machine using this protocol, in my example, we run it on 3 VMs, very flimsy VMs. In a non-failed case, when everything is fine, we were able to get about 13,000 requests per second or so. When you fail just one machine, one node, algorithmically it should be just fine. It should be safe and should continue working. The authors show that it will be safe. The authors show that it will be live. It's just not live enough. Right? So in this case, the performance dropped by a factor of 5, more or less. Right? So this is as good as that. We want to design for practical fault tolerance, not algorithmic paper fault tolerance, right? And key kind of ideas here is we need to make sure that our fault tolerance, our reconfigurations that our systems will take in response to faults, they don't take a lot of resources, right? They need to work under stress. They need to work under load. I can give you kind of briefly another example. If I go back to multipaxes, right, or Raft, those algorithms that are actually used in practice, their reconfiguration, their failover from one machine being a leader to another machine being a leader is not cheap either. Because when this happens, you need to have another round of communication, and you need to move the data to make sure that the new leader is going to be the most up-to-date. That happens in multipaxes, or move data from the new leader to essentially redo a bunch of stuff if you use in Raft, right? But those reconfigurations will move data, the data that those systems are supposed to replicate again, right? So it has been replicated, it has been moved once through the system, and the reconfiguration will potentially make you move more data, repeat stuff, right? It's not cheap. This is still better than this because once it's done, once those algorithms are done, multipaxes and Raft, their performance, even if they only have 2 out of 3 nodes, their performance will go back up, right? So they will stutter for a little bit, and then they will continue working normally, or almost normally, because in reality we still need to replace the failed replica, build that failed replica, copy the data, make sure it's caught up, which again takes the resources from from the algorithm, right? But it is better than this, and that's why those ancient algorithms from 1980s are still kind of the state of the art in the database world, for replication. Okay, So step number 3, avoiding the over-optimizations on common paths. This can be somewhat controversial, but we like to optimize things because we think that this is the only way our system is going to be used. If that changes, right? If you run your exception path more frequently, if something happens to the workload, well, now you can spend all of the resources on that exception path, essentially degrading the capacity, the performance of your system, right? So I'm not saying not to optimize things, but I'm saying that you need to optimize not only the common paths, but also things like those reconfigurations and recoveries and error handling and so on and so forth. Because when those things, for whatever reason, start to dominate, you don't want to waste too much resources on them. Step 4, workload engineering. Right? So this ties back to, do we have hotkeys in our system? Can they impact our transactions? Do we have some kind of coordination between the users, whether the users explicitly coordinate or not? Right? Can that impact our systems? Right? So, if you're running a database, if you're working with transactional systems, the workload engineering, trying to avoid the hotkeys, trying to write, you will need to write your applications to avoid the hotkeys, right? If you're doing a retail, setting, for example, let's look at the retail example, on Black Friday, right? You probably don't want to update the inventory count with every order checkout, because that one particular field for some very hot discounted item is going to be the point of contention, right? You will need to design the workloads around having to touch those highly contented keys or objects very frequently. Finally, the last part of being okay to be metastable is what happens when the trigger resistance is not enough, right? As I said, we cannot eliminate all the triggers. We can just make our systems a little bit more, tolerant to some of these triggers, right? But they can still, exist. They can still create really bad situation for you. They can still cause the overload and whatnot. So at this point, we really want to try to stop the feedback loops from development, right? So if you're already in a failed state of some sort with that very expensive trigger, at least try to avoid developing those amplification effects. And it happens to be the case that in systems we tend to have some components that are more vulnerable to these problems than others. And these more vulnerable components, they tend to be stateful components, right? Your databases, data stores, distributed file systems, publish-subscribe systems, and so on. And they are more vulnerable because they are very difficult to scale, right? So if you have a stateless microservice and can get some additional capacity, well, you can scale that one easy. If you have a stateful service, stateful component, even if you have the additional capacity to scale the stateful distributed database, you will need to repartition your system. You will need to move the data around between all of these partitions and whatnot. And all of that, again, takes the resources. Those reconfigurations takes the resources. And if you are overloaded because of a trigger, you don't have those resources, so you cannot really scale your way out of the system, out of the problem. So we want to protect those stateful components. We don't want them to fail, and we don't want their failures to kind of propagate through the rest of the system. So I'm going to give a very high-level hypothetical example, right? So maybe we have some service 1, service 2 in a database, and just requests go from one to another. And if we start to overload the database, right? So the database starts to get overloaded and take more time to respond. More things are going to start to queue up at that service right in front of the database, the service that calls the database. Maybe that one will start to time out as well. It may also start to have some feedback loops of its own, right? So it may start doing retries against the database that's overloaded. It may have the garbage collection loop that I talked about. So like multiple mechanisms, multiple amplification loops can get activated once we get to this situation. And the reality is, like, most systems, most apps are not going to be that simple. So you may have some other requests that may not even touch the impacted the database, but may share some other services, right? This may be impacted because we just like propagated some of that failure from the vulnerable component that is failing, that we cannot scale, down to some other service and whatnot. So the solution is load shedding, right? This is something that we'll have to do if we get to metastable failure state anyway. We'll have to turn it off and on again. Why not do it earlier, right? Protect your vulnerable components. If you load shed, right in front of the database, right in front of the overloaded stateful component, you can get its load under control. And if that component is perfectly healthy, right, now you can scale it if you have that capacity, because now you may have the resources in that component to actually start doing those copies and repartitioning and so on. The two big questions, of course, is like what to load shed, right? Can you identify exactly the things that need to be dropped? What work do we need to drop? It may be easy to say, okay, just drop the work that's going to overload that particular database, right? But real systems are more complicated than my toy example. We may have caches, we may have like a bunch of other things sitting between, some service and a database and a stateful component. So sometimes you need to prioritize what you load shed in a way that actually helps your system to recover, right? So you may prioritize it in such a way that will prevent your system from recovery. So this is a difficult question to ask, and I don't pretend like I have a good answer. I have some hints, and I'll be like, willing to talk offline on that, but I don't think I have a really good answer. And the second question is like when to load shed, right? Of course, we can do it right in front of the vulnerable component that's about to fail, right? But maybe if we know what we're going to drop, what work we're going to drop, maybe we can drop it earlier, right? Just save us a little bit of resources. And so luckily I got to the end of my talk, right? And I just want to reiterate one more time. It's okay to be metastable vulnerable, right? But we want to minimize the risks of going from that vulnerable state to the failed state, right? And we do so by protecting the vulnerable components and by practicing the trigger-resistant design or trigger-resistant architecture. Thank you.